Hello and welcome everybody to this video where I'm proposing you to go through the necessary steps that will take us from Ampere law to Kirchhoff current law, one of the basic fundaments and the background of our course on EMC. Let's work around this. So Ampere's law to Kirchhoff current law, or what are the basic assumptions and the basic steps that we need to take to assume this. The hope of this derivation is that if you're aware of what are the basic assumptions we need to take in order to arrive to Kirchhoff current law, starting from Ampere law, then it will become clear what are the mistakes that we are prone to do if we apply blindly Kirchhoff current law. That's the basic idea over here. So as we say, to start our derivation, we simply start with Ampere law. It's easier if we start with the Ampere law in differential form. So we know that the curl of J equals conduction currents, sorry, the curl of H equals conduction current J plus the time derivative of the displacement field. Some people also call this term JD. You will find that sometimes J sub D to represent displacement currents. Now I'm going to do a very simple operation. I'm going to take the divergence of Ampere law, both sides. So the divergence of the curl of A equals the divergence of J plus d dt. And we know from math, some mathematical theorems tells us that this always equals to zero. Why is this always equal to zero? It's nothing to do with the physics. Of course, it has to do with the physics, but why do we know this is zero? It's just a purely mathematical thing. All the rotation of any vector field is always solenoidal. That's a theorem mathematicians can prove. Before we go any further, let me a little bit talk about what we think what J is. So let's have a piece of metal in the shape of a conductor. So you have a conductor like this, and this conductor of a certain cross section, doesn't matter how, is the cross section of our conductor is carrying a current density J that can have any shape in general. J. So J can have some components in line with the conductor, some components orthogonal to the conductor, some components swirling around the conductor. It doesn't matter. It's a general vector of current densities distributed in a piece of metal. So the idea is to try to estimate what is the net current flowing through the cross section of my conductor. That's what is important, because that's the current that will be actually useful, the net total current. So what I need to do is I need to define the cross-section area of my interest. So we call this A. For instance, this cross-section of my conductor. And to know what is the total net current flowing through that surface area, I need to perform a very simple integral. And that integral is the surface integral on area A of my current density J with integration element ds. And now ds is a little vector that is normal to the surface of interest. Is normal to the surface of interest. It can point out or it can point in. It doesn't matter. I will just have a opposite sign for my current. So it's basically a flux integral what I'm calculating over here. So the total net current will be just the surface integral on a cross section of interest of my current density, and that will give us I. So this is just a quick reminder of what this J is about. how we move forward? Well, let's try to think of a somehow realistic scenario where we are in a circuit node. You know what a node is? A node is these points where two or more branches meet. But now I'm going to try to draw this sort of in a 3D way. So we have three conductors flowing in a node, and this node has a volume. Let me see if I can be clear. So this is one conductor, this is another conductor in a node, and that's another conductor in the node. So this region that you see here that I can try to draw some lines. I hope it's more or less visible. So this is my node. It's certain volume. That this node has a certain volume V, and there's also a certain surface enclosing that volume S. And we have conductor number 1, for instance, flowing here, and conductor number 2 here, and conductor number 3. And each one of these conductors are carrying some current densities. So we have J1, for instance, flowing in conductor 1, and we have J2 current density flowing conductor number 2, and we have J3 the current density flowing in conductor number 3. I only draw 3 conductors flowing in, but of course this can be any number of conductors meeting in the node. This is the volume we're going to try to investigate, and what is going to happen there. So let's do that. Let's pick up this result we just got. The divergence of J plus dd dt, and integrate that in this volume V, the volume of my node. We know this has to be 0. Oh, sorry. This has to have a dV over there. Okay. We know this is equal to 0. Why do we know that? Well, because the integrand itself is already 0. So the integration of 0 has to go to 0. Now I'm going to split this integral before we split, sorry, I will apply the divergence theorem. So you know that I can transform this volume integral of the divergence of a certain vector field into the closed surface integral on the surface S, and now the surface S is a surface defined by this node over here. So I'm here trying to paint surface A. Surface A will have 3, say, circumference where each conductor meets the node, 1, 2, and 3, and then the whole volume of my node. This is a surface A that is enclosing my volume over here. So I said S here, but I should write down A. There you go. This A is a closed surface. Right. So I said I'm applying the divergence theorem. So the integrand now is just J plus the ddt in the ds, and ds is a series of vectors. Let's close this just for clarity. This is a dot product. And ds is a series of vectors that is always pointing normally to my surface, the surface of my node. So for instance, in this whole phase, the ds will point upwards like this. In the phase where conductor number 3, for instance, meets the node, my ds will point in this manner. In the conductor number 2, it will point in this manner, so we can call this ds2, and this ds3, and this we call that ds1, and we can call this ds upper, and on the low side, on the side of the node that is not visible now, we will have a ds pointing downwards, something like that. You get the point. So we can build this integral with 1, 2, 3, 4, 5 surfaces, or even 4, because up and down are simply connected, so it could be the same thing. It doesn't really matter because at the end that integral will go to 0. So there are many ways how to define this. We are still under the circumstance where this is equal to 0 because I did nothing but applying the divergence theorem over here. Now I'm going to distribute this integral, and then it becomes the integral of j on a closed surface, ds. Remember, my ds is the collection of all these partial ds, ds1, ds2, ds3, so on and so forth, plus the closed integral on A. We call this A, area, surface, yeah, messing up there, no problem. dt dot ds. This equals 0. So let's break down the first integral over there. So it's clear that the total closed surface of my node can be broken down into a combination of many different surfaces. The first one will be, for instance, S1. Now this is not a closed surface anymore, it's an open surface. So this is ds1. So I'm going to integrate j, but in this particular case, the j that matters is only j1, because it's the only non-zero current density over there, ds1, plus the surface integral on S2, following the same logic of j2, I should say, ds2, plus, and then here I would write the integral of j3 and surface 3, etc. But allowed me to j for anybody, because I could have done this for n conductors. So in general, I will have, if I have n conductors, in my case, n is 3, but it could be any other number. So this integral can be easily generalized this way. So we have n conductors, each one carrying a current density, and the surface integral of this current density on the face that meets the node is the total net current that enters or leaves the node. Then I still have to add this closed surface integral on the whole thing, A, dt dot product ds equals 0. Now, in view of the above, look at the quick reminder we did here. If we have a conductor, that conductor can have any current density, but the net current is found as the surface integral on an area that is the cross section of interest of my conductor, and that will give me the current, the total net current in that conductor. So I recognize that that integral is exactly what I have here. So this whole thing will be just I1. What is I1? Well, it's just the net current flowing in conductor 1. Similarly, this will give me I2. What is I2? Well, just the net total current flowing in conductor number 2, confined in that conductor. And this will be IN. So I can very simply rewrite these integrals as the sum of all the net currents flowing in or out a node plus this surface integral, which is bothering us a little bit, but we will get rid of it in a second. There you go. This is equal to 0. Now this looks pretty much like Kirchhoff's current law. The only assumption so far we have done is that conduction currents, all these J's, are totally confined inside conductors, which is not a rare assumption. I mean, most circuits will obey this very clearly because conduction currents can only happen in metal unless you have your node immersed in a conductive liquid or gas or medium. Then that assumption will fail because you can have conduction currents everywhere. But for 99.999% of the cases, this is a very fair assumption, not crazy. That is to say, to assume that conduction currents are only and exclusively confined inside the conductors. That's not a problem. But here, this term is a problem because to really get to Kirchhoff current law, we need to get rid of this term over here. And one way of getting rid of this term is to integrate in a zero surface, but that's the trivial solution. The other solution, which is not trivial at all, and it represents the basic assumption to get from Ampere law to Kirchhoff current law, is that we need to make this term go to zero. In other words, the assumption is that if this is a vector 0, dt should be 0. And we know we only get this under static or quasi-static conditions. Only under static or quasi-static conditions we can safely assume that there are no displacement currents, so the dt equals 0, and then Kirchhoff current law is valid. We are neglecting possible couplings, parasitic. We normally model this with parasitic capacitors towards the environment. There's some environment here. Let's say there's a chassis ground over there, or even parasitic capacitance between a conductor and one conductor and the other. So we are neglecting all these displacement currents. In many applications, that's safe to neglect. Not a big problem, but not always. And when you neglect things that then appear, well, that's a call for problems. So that's the whole message of this calculation. I hope it was clear for everybody. In the next video, I'm going to do a similar thing to go from Faraday law to Kirchhoff voltage law.